This is one of nature's most relentless forces, a river, carving its path with raw, untamed energy. For millennia, it's shaped the very world around it. So to build a megastructure right in its heart, to harness its power for all of us, engineers must first do something that sounds impossible: stop the river in its tracks. Before a single cubic meter of concrete is poured, engineers have to solve a problem that sounds impossible. How do you build a structure in the middle of a river without the river destroying it while you work? It's a multi-year struggle against water and time that most of us never get to see. This is the story of how engineers temporarily redraw the map, fighting a battle against physics itself to lay the groundwork for some of the largest structures in history. Long before the first truck shows up, before a single scoop of dirt is moved, a dam begins with a question. How can we power millions of homes, secure water for farms, or protect towns from devastating floods? The answer often lies in the incredible potential energy of a flowing river. But figuring out where to build is one of the most critical decisions of the entire project. Engineers can spend years on reconnaissance and feasibility studies. They send out teams of geologists, hydrologists, and surveyors to read the landscape. They comb through decades of streamflow data, map the terrain with laser precision, and study seismic charts to understand the forces hiding underground. They are searching for that perfect spot, a foundation of solid rock that can support millions of tons and a valley shaped just right for holding a massive reservoir. This first phase isn't glamorous. It's a slow, painstaking process of collecting data and weighing risks. But the success of a multi-billion-dollar project hangs on getting this part right. A single miscalculation here, a misread of the geology, could spell disaster decades later. They aren't just planning a building, they're planning a permanent change to the natural world. And every variable has to be accounted for before the real work can begin. Once a site is chosen, the first colossal challenge begins: creating a dry workspace. You can't just pour concrete into a flowing river. You have to get it out of the way first. This is the river diversion phase, and it's often one of the most dramatic parts of the whole construction process. Depending on the river's size and the terrain, engineers have a few tricks up their sleeves. For some projects, they carve enormous diversion tunnels, sometimes over a mile long, straight through the solid rock of canyon walls. For the massive Itaipu Dam on the border of Brazil and Paraguay, workers spent years carving a 1.3-mile-long diversion channel to shift the mighty Paraná River. The amount of earth and rock they moved was staggering. A more common method, though, involves using cofferdams. These aren't just simple walls. They're massive, temporary dams built to hold back the full force of the river. They can be made from mountains of rock and earth or interlocking sheets of steel driven deep into the riverbed. A cofferdam essentially splits the river, creating a dry, protected pit where work can start on one side while the water flows on the other. For the Three Gorges Dam, engineers built a series of immense cofferdams to section off the powerful Yangtze River, allowing them to work in stages. This is a temporary fortress of steel and rock, waging a constant war against the immense pressure of the water it holds back. With the river held back and the work site pumped dry, an almost alien landscape appears: the riverbed, scoured clean over eons. But this exposed ground is rarely strong enough to support a megastructure. What comes next is one of the most critical, yet hidden parts of the process: preparing the foundation. Crews start by digging out all the loose sediment, soil, and weathered rock. They scrape and blast their way down until they hit solid, competent bedrock. A dam is only as good as the ground it stands on. If the foundation is weak or porous, the entire structure is at risk. Once they hit good rock, the work becomes almost surgical. They meticulously clean out any visible cracks and smooth over uneven surfaces with specialized concrete to prevent stress points from forming. But the real magic happens deep underground. To ensure water can't seep under the dam, which could undermine its stability, engineers use a process called grouting. They drill a grid of deep holes into the bedrock and pump a cement-based mixture called grout into them under high pressure. This grout flows into the tiniest fissures, sealing them for good. This creates a grout curtain, an impermeable underground wall that extends deep beneath the dam's foundation, blocking any potential paths for seepage. This painstaking work ensures the dam will be anchored to a solid, stable, and watertight base. Only now, after years of planning, diversion, and foundation work, can the main event begin: building the dam itself. A common myth is that a concrete dam is poured all at once, like one giant block. The reality is far more clever and complex because building something the size of a mountain means fighting a fundamental law of chemistry. When concrete cures, it generates a huge amount of heat through a chemical reaction called hydration. If a dam were poured as a single, solid piece, the heat trapped in its core would become so intense it could cause massive cracks, compromising the entire structure. To prevent this, concrete dams are built in a series of separate, interlocking blocks, or lifts, often just a few feet high at a time. The logistics are mind-boggling. On-site concrete plants work around the clock. To build the Itaipu Dam, a network of cranes and aerial cableways moved over 12 million cubic meters of concrete. To manage the heat, engineers might use special concrete mixes that generate less heat, or add chilled water or ice to the mix to cool it down from the start. For huge projects like the Hoover Dam, they embedded a network of steel pipes inside each concrete block and circulated ice-cold water through them, drawing the heat out as the block cured. Once a block was cool, the pipes were filled with grout, bonding it all into a single, monolithic giant. It's a slow, methodical process, a battle against thermal stress to ensure the dam hardens into an incredibly strong and durable structure, free of hidden flaws. After years of construction, with the colossal wall complete and the turbines and spillway gates in place, the moment of truth arrives. It's time to let the river back in. But this isn't a dramatic, one-shot opening of the floodgates. The diversion tunnels are sealed, and the cofferdams are often removed or simply submerged. Then, slowly and carefully, the river is allowed to rise against its new barrier for the very first time. This first filling of the reservoir is the ultimate full-scale test of the entire project. Engineers watch thousands of sensors embedded in the dam and the surrounding rock, looking for any sign of seepage, unexpected movement, or stress. It's a period of high alert, the final exam, after a decade or more of work. As the water level climbs, a new lake is born, and the landscape is changed forever. The impact can be monumental. For many communities, a once unpredictable river can become a source of stable, clean, hydroelectric power. Water is stored for cities and farms, providing a reliable supply through dry seasons. Downstream, people can be protected from the threat of catastrophic floods. What started as a battle against nature can culminate in a new kind of partnership, a tamed force, now working to power the future. It's a transformation that takes years of unseen effort, all to create a structure built to stand for centuries. The finished dam hides nearly all the secrets of its creation. The diversion tunnels are plugged, the cofferdams are gone, and the perfectly prepared foundation is buried beneath millions of tons of concrete and water. What's left is a quiet monument to an incredible engineering journey. If you enjoy documentaries about amazing engineering and mega construction, be sure to like this video and subscribe for more. What part of this massive process did you find most impressive? Let us know in the comments below. From carving new paths for rivers, to fighting the laws of chemistry, taming a river is one of the greatest challenges an engineer can face. These projects are more than just concrete and steel. They represent our relentless drive to solve huge problems and build a better future, one monumental block at a time.